called Bangalore Apache Storm Meetup. So how many are first time here? Okay, so we have around 50% maybe. Right, so today maybe less people. I think there are a few reasons behind that. One is that we are clashing with many of the meetups today. The reason not being we scheduled on this day. Last week was one, so a lot of meetups got postponed to the this week. So we are clashing with JS channel and even other Spark meetups. The second is maybe we are doing a lot of videos, right? So people are saying, okay, we can just watch the videos and in home. So that's also fine. So how many of you watched earlier session videos? Okay, so most of you are catched up, so that's good. So let me just tell you, because there are few new people, like what is our meetup is all about and how we differentiate from other meetups. So how many of you been to other meetups, like any other meetups, Hadoop meetup, JS meetups? Okay, most of you. So you know what is a meetup is. So the differentiation is there are three things we differentiate. The first thing is we focus on hands-on. So this is kind of a thing we are trying to do, which means the first session normally we will not only talk about technology, we want people to come and do some hands-on so that they get a feel about it. So that is the first kind of a thing. The second thing we want to do is that kind of a community-based effort, where people from different companies, different backgrounds come and give sessions. So that's the kind of a thing. And third thing we are trying to do is that little bit longer sessions. So these are not really flash talk kind of things. They are not 20 minutes kind of things. So normally it's like an hour or two for a hands-on and maybe an hour for just sharing the experience. So this kind of gives us a flexibility to spend time and really understand things rather than just skipping over the content in a very, very fast way. So these are the three things we are trying to differentiate, and also we want to do it regularly. So this is the third meetup we are doing in last 3 months, and the way we are doing is that every last week of the every month. So that's kind of thing we are doing now. It's easy for us to remember also. And also a lot of companies are coming forward and giving us the nice place. So we are hosting third time in the APAG. So we have to give a lot of thanks to APAG guys also. So we have 3 sections to the talk. The first section will be introduction to the Spark streaming. So where we have going to have a hands-on. There is one talk from one of the APAG guys itself. We will talk about that after our session. And we also have this idea of flash talks. The flash talks idea is that if someone done anything in Spark or related technologies, and if you want to share your experience, you can come forward and tell here. So you don't need slides, you don't need any kind of form of preparation. If you want to share, okay, this is how I did, or this is the way we are doing inside a company, if you want to share, you have those slots also. So you can take maybe 15 to 20 minutes. So these are the 3 different things we want to do. We didn't have actually any flash talk in the last 2 meetings because I was taking a lot of time, right? So it was running over the time. So this time we are trying to make a small session so that if really someone want to come forward and share the experience, we want to do that. Okay, so this is kind of an overall idea about what is our meetup is all about. Let's get started with the first session. It's an introduction to Spark Stream. Next. Okay, a little bit more about me. I think if people are coming from last 2 times, you know a lot about me, but just for the first time. So my name is Madhukara Phatak. I run a company called Data Mantra. I am a particularly consultant in Hadoop, Spark, and surrounding technologies. I am working in Hadoop around now 5 years, and I do enjoy doing meetups and talks. That's kind of thing. And if you want to connect with me online anywhere, you can go to this website. You will find me in Twitter, LinkedIn, and all other places. Okay, so the idea behind Spark streaming is kind of a natural extension to the talks what we have done earlier. So if you have seen videos or if you have been to earlier meetups, we extensively talked about Spark and Spark RDDs, right? So as people were saying, okay, what is next? So natural progression was we want to go to streaming part of it. So we already seen the batch processing API. We want to see the streaming part. Now a lot of people asked me last meetup actually that why we went to RDD, advanced RDDs even before we went to streaming. Because people are saying, okay, we done the introduction to batch, let us do the introduction to streaming, then we go to the deeper thing. So at that time I told people that abstraction of RDD is very powerful and it is not limited to one API. So that's what we want to see today. Even when you do streaming, so the same abstraction what we learned in last 2 weeks will come back to you. So that is kind of a thing what we want to show. And also another thing I want to say is that this session is kind of very introductory. So how many of you worked in streaming before? Even in Storm or Apache, like Spark Stream? How many? Okay, only a few here. How many of you worked in the bash mode, like MapReduce, Hadoop, Hive, Pig? Okay, most of you. So I think most of you have the background of bash processing, not really maybe doing the streaming part. So that's why I have kept little bit introduction initially, just to get your feel that why you want to do streaming and why world is moving towards streaming. Right? If you see more and more companies, they want to do streaming, then they want to go back. So that's kind of a trend. So we want to give like what is the idea behind why people want to go streaming. But more powerfully, whatever we learned in last 2 meetups, it will all come back to streaming also. So same RDD, similar abstraction we will see here. So this is kind of overall agenda, and we are going to run few examples. And the way we are going to run examples is a little bit different, because last time we had some issues with IntelliJ and all the setup. This time it is also possible to run from command line. So if you have issues with the IntelliJ, you can skip the IntelliJ, run the example from command line, and you should be happy. So that's the overall idea. So that's the overall agenda. Yeah, next. Now, if you ever been to any sessions of introduction to big data or any introduction to any big upcoming technology, there is always this 3 V's, 3 D's, those kind of things. And this slide has actually 2 different use cases. One is, everyone knows 3 V's of big data, right? Volume, velocity, and the variety, right? So these are the 3 things. And also this kind of shows you, like I told you, one of the thing about our meetup is giving incentive for people who are repeatedly attending. And if you see, the way we are covering the sessions is this order only. So what is the volume? So volume talks about how much size of the data we have. Yeah, I can come. Right? So how much size of the data becomes. So this is the way I think everyone starts with. So people inside a company say we have terabytes or even gigabytes, terabytes and petabytes. We want to process the data. We have a lot of files sitting around. We want to process the data. Now, what I also want to talk about is what is the part of the big data pushing what part of the big data ecosystem. So when you have a volume, the batch processing system are getting pushed, right? All your MapReduce, Hive, Pig, those kind of systems are getting pushed because you have a more and more volume things. And this is what we have talked from last few weeks, right? So kind of saying, okay, when we have a lot of data, we want to process it on the distributed system. So this is what we call volume. Now, big data is not just characterized by the volume. This also, there is 2 other parts to it. So these are one of the parts we are going to talk today is called as velocity. So what is the velocity? So velocity is lot of data coming in very, very small amount of time. And also you want to process that in very small amount of time. It's not just lot of data. It is coming in very, very small time. And also you want to make decisions in very small time. So which means now big data has another dimension. Not only you are getting a lot of data, the amount of time you have for collection and doing decisions also very, very small. Which means you cannot use your existing batch processing system to do it because there's a lot of latency. Now these kind of velocity part of the big data pushing this streaming applications. So which means in every ecosystem, Hadoop, Spark or anywhere, we are seeing new kind of tools coming in for doing streaming specifically. Is that they are not like modified batch processing system. They are the new systems which can handle this velocity, not only just the volume, velocity also. Make sense? So that is the second thing. The third thing is also obvious to us, this variety of data, right? We are no more living in the ideal world of RDBMS, where everything is structured. We have structured, semi-structured, unstructured, JSON, XML, so many things coming in, and there's a third part of the ecosystem getting pushed. This idea of having a SQL, shell script based things, we want to do, not just the way we do in MapReduce and those kind of things. So if you see in the Hadoop ecosystem, we have Hive, Pig. If you see in the Spark, we have Spark SQL, data frames and those kind of things, where it's not just about volume or velocity, we have this variety. What happens is that, okay, I want to handle SQL, I want to handle JSON. So there are specific systems built for different needs. So what I want to try to tell you here is that big data is not just about size of the data. That's the thing what we start with, right? So it's just not just the size of the data, it's also about velocity and the variety. And we have spent a lot of time doing the volume. Let us talk about the velocity. Right? Why we have to care about velocity. And a lot of people have not done the streaming before. So I just want to give an idea of why velocity matters. Right? Now, next. Now, I think everyone who are in science, in any point of time, you know what is a velocity, right? So it's I think it's a distance divided by time, right? Okay, if you are wrong, then you can say. But here, the velocity means very specific. Now, people think velocity means just amount of data they are collecting given time. Right? So if you are getting a stream of data, maybe from log file or maybe from your mobile application, if you are collecting a lot of data in a very small amount of time, people think, oh, we are doing some kind of stream. But I say it is not about just collection. Are you doing processing also at the same time when you are collecting and doing some decisions? Because a lot of companies, where they say streaming, what they normally do is that they collect a lot of data, dump into HDFS or any kind of database, and they run like maybe hourly or maybe daily batches. So that do not really comes as a velocity. So velocity means both how much time you take for a collection and at what speed you are going to calculate the actual data also. So this both combination collection and processing, we kind of say velocity in big data. So if you just collecting the data, you are not really doing things. So its collection is okay. You are collecting data and dumping it in maybe in a bigger storage. But if you are also doing processing at the same time, then you qualify to this facet of the big data. So this is the one you have to be very clear about. And also, this is the one trend we are saying these days. One of the reasons why Spark became famous initially, one was this in-memory idea, where you can keep data in the RAM and do the processing, but also this idea of streaming, that you can do computation when the data is moving. So the first people who adopted Spark is kind of okay, looking at the Spark streaming. Now the question is, why more and more companies moving towards this idea of streaming rather than just a batch? Nowadays the trend is like this. We do a lot of decisions on the streaming and we dump the stream data into some storage, then we will do some deep analysis. So it used to be we dump all the data into the storage, then we do deep analysis. But nowadays you do a lot of processing on the fly, we will call it as doing processing on the wire. Then as a backup, you store it in the disk. And if you go to any company these days and ask, okay, what kind of things you are doing, they say, okay, we want to do more and more in real time. We don't want to wait for maybe even hours or days just to get the result. So this is kind of a trend. And also, what is the primary driver? So these are like what I am giving is the consumer facing. If you go back to enterprise, there are a few other. One of course is social media. In social media, there was one nice talk by one person saying, in Twitter, our attention span is around 8 seconds. When we see something, we react to it, then we move on with some other things. Right, so we only have some time to react to it, which means whatever the calculation or processing you are doing, you have very, very less time. So social media is driving this real-time thing, which means I updated something I want to see within few milliseconds. Okay, I want to get famous within few milliseconds. So right, there is always a drive of at that point of time. And a lot of things in social media lose meaning after some time, because you need to have the content. Let us say, I think a lot of people are following IPL. If you have some status update about IPL, that movement, it is hard, right? Everyone has tea and everyone will comment. After 2 days, you have new match and new things. It do not have any meaning. So social media is the biggest driver. Second is, after big data, the next new trend is IoT, right? This Internet of Things, which means everything around you emitting data. Maybe your router, your watch, maybe your shoes in the long run, everything around you sending some data from your nearby places. And what happens is that this data is very, very specific. They know where you are, what you are doing, all those kind of things. And these are very small sensors. So they keep on sending the data, because them itself, they don't have much storage. Right? They cannot store for more time. So they keep on sending the data. Now what happens is that this all data is real time. All data is coming to you in the real time, and you want to make sense out of it. For example, if you have a company called Nest, they do this thermostats, which keeps on sending the data, and depending upon the data, they make decisions that should you decrease the temperature, increase the temperature, those kind of things, which is very, very specific to that point of time. You cannot say, oh, I analyzed your temperature 1 hour back, now I'll increase your temperature. Maybe the whole weather is changed and you have to recalculate. So the idea of Internet of Things, where the things are connected and everyone is emitting so much amount of data, is also very, very important. And third thing, which is not normally obvious, is this idea of mobile applications. Right, so again, with the mobile applications, everything is instant. So I was talking to one of the Flipkart guys recently, like on the, they are moving into a new platform altogether within a company. I was asking, what is the overall idea? Like, why you want to move into something new? They are saying, earlier, when they were like 2 years back, they had this idea of downtime. So what they do is that since Flipkart is operating in India, so downtime is night 2 o'clock to 4 o'clock. So the people will come in, they will change the code and upgrade or whatever the things, then they will deploy and the new thing will come up. Now they say after they deploy the new application on phones, they really don't have downtimes. Which means at 3 o'clock someone is buying something, and if something goes down, they have a bad customer experience. So which means the new policy is zero downtime. And if you ever have any hit mobile application, the same situation arises. Particularly if you are global, then it's more worse because everywhere people are up and running. Even if you are regional, people are always there with the phone. Maybe someone will get up at 2 o'clock and say, oh, I need to buy something. Let us order and then sleep. Right? So what is happening is that with the mobile applications, again having to be up all the time and also doing decisions on that point of time also become more and more critical. These are not only just the first two, the social media and IoT are normal suspects, we kind of suspect that, but even with the mobile application trend, where always connected idea, right? Everyone can do anything at any point of time. This idea of doing decisions at the right time becomes more and more important. Now, next. I want to give you some specific use cases just to get an idea like how much important it is. So you can say, okay, maybe I don't do real time. Let me store the data and I'll do batch thing. What I will lose, right? That kind of thing, right? Maybe most of the time it's fine, but I want to give you a few use cases where it is so critical to the business. If you don't do in real time, there is no business. So one example is Twitter. So one of the main driver of the real time processing in big data comes from Twitter. The reason is Twitter exists for real time data. If you remove the real time part from the Twitter, there is no meaning to those data. So as simple as that, which means company stands on the idea that if they can do processing on real time, they are there. If they are not able to survive. For example, I will give you that they have to crunch billions of tweets per second. They are not just collecting it. Of course, they are collecting a lot more than that. But they have to crunch these billions of tweets per second in order to say what is trending on the Twitter. So if you have been, so how many of you are on Twitter here? Okay, how many of you know what is Twitter? Because if you watched any cricket match, there is like this hashtag, right? Tweet on hashtag, you can ask the captain. So many options are there in Twitter. So what is the idea here is that they say what is trending. Maybe Tendulkar is trending, maybe IPL is trending, or some movie is trending, something is trending. Now the trending comes with very, very small window. If you just go after half an hour, the trending is gone. Something else is trending. Which means they don't really have a much time window in order to collect the data and process and give it to you saying that this is something people are talking about now and you have to pay attention. So the whole idea of Twitter just stands on top of the idea that they can do a lot of things in real time and give you valuable information at right time rather than keeping you maybe waited for next. If you are not Twitter, then you have to go to news channel and say, okay, what's happening? But they are like 1 hour, 2 hours late always. Right? I mean the web, not the video, but if you can't watch video so much, right? So Twitter needs to be like that, so which means the whole company stands upon this idea of doing real time. So in these companies, real time is not optional, it is critical. So second thing, I think also people may not know much is that credit card companies, they were doing real time from long. The reason is that they have this idea of fraud detections. Right? For example, you are having a credit card and if they think you are doing the front transactions, they want to know at that point of time and deactivate your card. Not, they cannot say, okay, we collected the data, after one day we thought some fraud was there. By that time, maybe that person has taken all the money out of your credit card. Right? So if you see this example, right, it is very, very critical because we are talking about money here. Right? So in the credit card companies, they have this real time where they collect a lot of transactions around millions per second. Maybe more if you see companies like Visa or MasterCard, and they have to detect is there any fraud within a few milliseconds, and they have to give some action. Maybe action is calling the person and saying, okay, are you using the card? For example, these days Visa do it. For example, I was paying some money where they don't ask the CVV and those kind of things, and they just call up immediately and say, okay, are you really using this card? Otherwise, they will not authorize the transaction and those kind of things. So all these are automated; they are not done manually. Which means in these companies, you have to do real-time processing in order to really get the business going. It's not like, okay, we can wait, because if you wait for some time, whatever the things you have calculated may not be useful. Now these first two examples are very kind of, we say, business critical. But now I want to give you some other examples where you may not think it is so critical, but if you see the earlier trend, you see why it is important. For example, I think everyone is on WhatsApp these days. It's like a new Facebook, right? So everyone asks on WhatsApp. And if you think about WhatsApp, you may not think they have to do real-time analysis. What WhatsApp does is, okay, it should send real-time messages, that is there, but do they need to do some real-time analysis? What they have used to do is that when the WhatsApp is down, so they used to have this manual idea and go and figure it out, okay, something is down, we'll fix for it. But as number of users are increasing, they have very difficult time. One of the examples I have to give is that WhatsApp went down for 2 hours, around 11 o'clock at night, that's Indian time, and they lost around 5 million users to Telegram in those 2 hours. So if you see the kind of a trend, again, because they are global of course, and they are there on every platform, what happens is that even the 2-hour downtime for a company where maybe real time is not really critical, they are losing so many millions of users. And if you go to, I think everyone maybe seen a big billion day in Flipkart. And I'm just giving an example where people can understand. So many people went to Amazon because they were able to buy something, right? So you already made up your mind that you want to buy something today, and if Flipkart is not giving the experience, let me go and buy somewhere else. Which means it's not only that you have to do business in the real time. Sometimes what happens is that may not, if it's not obvious to you, right? You may be losing the business because you are not able to recognize there's some problem. We can give them a few time. Maybe they understood maybe after 1 hour that there is a problem, but even in small window, you may lose a lot of customers. Because nowadays, making a switch is very easy, right? What do? You install a new app, or you go to a new website, start purchasing or start doing whatever you used to do before. Right? So what happens is that even if you have non-critical business, where mobile application, these days analyzing the application and making sure that it's always high available and it's also, maybe some part of the things are not working. You have to recognize it and fix it even before you start losing the customers. So what happening though, this is why more and more people are moving to real time. The reason is that there's expectation always that things are always running, and people want to use any point of time. There is no idea of downtime, which means you want to keep on monitoring the system, or maybe keep on doing some analysis which gives you some idea saying that okay, something has gone wrong, we have to do some actions. So that's why more and more companies are moving from the idea of batch processing into more and more real-time analysis. All are able to, and one more thing is that my slide don't have this slide called any questions. So if you have any questions, you can ask in between. Okay. Next. Now, what we want from the real-time analytics. So these are kind of requirements from the real-time analytics. One is that ability to collect and process terabytes of streaming data. Now you can say, oh, terabytes is too huge, right? Terabytes is too huge. Not really. If you really think about any application, it emits around megabytes of data. And with the cheap data plans, right? So many things are getting sent. So terabytes streaming data is not a big deal at all. So you want to analyze terabytes of data, not only just collect, and also want to process and get some insight. This is one of the things. The second thing is that you also have an ability to get the data from multiple streams, because these normally do not come one stream. Maybe one is coming from server logs, one stream may be coming from your mobile application, and every mobile application normally has some web application part of it. Maybe it's coming from web applications, maybe it's coming from some IoT kind of device sitting in a home or some other place, which means the data is coming from multiple streams and you should be able to combine them. Maybe some part is coming from one place and some part is coming from other places. It's not only one stream, you want to get from multiple streams, combine it and process it. So this is the one of the requirements. And third thing which people don't really understand initially is that by that time, the data what you get in the stream is not rich, because it's about that point of time. You want to enrich that data with historical data. So if you see any real-time analytics, it's not only what you can get in that point of time, you want to combine the data, whatever you have seen before. For example, if you are doing fraud detection in credit card companies, you cannot directly take a transaction and say it's a fraud. You have to take the transaction, take what is the customer history before, combine that information and say, okay, this may be a fraud transaction. So combining the real-time data with the historical data is very, very important, because real-time data itself may not be rich enough to make the decisions. So this is also the third point. The fourth point is, when we do streaming applications, we have so many downstream applications we want to service, particularly dashboards and a lot of monitoring systems. Maybe they say, I calculated something, I want to send it to a dashboard where people can see and say, okay, something is wrong or not. Or maybe I want to send it to an alert system and say, you have to raise an alert, something gone wrong. So it's not only you want to stream the input data, once you get the result, you want to stream it back. It's not like you want to dump it somewhere and someone has to pick up from there. You want to have ability where you want to stream it. So this is kind of a overall requirements what people need from the real-time analytics platform. Okay. Now, before we go into Spark, we always have to talk about Hadoop. That is kind of always the way we are going to do. Because if people already done something with the Hadoop, so you have to know what is the thing you are not able to, or maybe the pain point, and how the new systems coming along going to solve it. And the same with we did with the Hadoop batch processing system. The same thing we are going to do with the streaming. Actually, for streaming, there's two parts to it. One is streaming on MR, and there is something called Apache Storm. So we'll go through. So how many of you done stream processing on top of MapReduce? Anyone done? Okay. So idea here is that you collect the data, you dump it to HDFS, and there will be a scheduler which will pick up the data maybe after some time and run the MapReduce on top of it. I think that makes sense. Right? So that is the way people used to do when Hadoop came along. Maybe I'm talking about 6 years back. Right? Now it is not a nice experience. The reason is that MapReduce was never built for real time. So by architecture, they say this is a batch processing system. And making a batch processing system work for us streaming is very hard. Right, so that is the one thing. The second thing is that MapReduce have an idea that always data has to come from disk. So which means you don't have any option. You cannot give a stream and say run the MapReduce on it. You do not understand. It has to say, okay, where is the data source? It has to be file. So that is another thing. And if you are going to disk, you are always late because you have to take a write and those kind of things. The third thing is that this is also important. When you are building real-time analytics, you have this idea of data pipeline, right? So you don't do only one operation and say you make a decision. You go through multiple stages and combining the results, you do some decisions. Now, if you ever done any multi-stage transformation in MapReduce, even in the batch processing, you know how difficult it is. You have this job control API where you have to say, okay, this is a dependency of this, and you have to make sure that everything goes fine. So, and also when you have multiple stages, every in between stages, the output has to be written into HDFS, again, which creates the more latency. So, where we have a stream, which is a multi kind of a thing by default, you cannot use a MapReduce where it's always slow for multi-stage. So, what we used to do is that combine all the coding of single MapReduce, so such a way that we can do everything. Now, problem is that then it becomes more difficult to maintain because we cannot remove and add new functionalities because everything is in same place. So, that is also the problem. The fourth thing is that you can say, okay, what about collect the data and run fast MapReduce, right? That is also fine. Problem is that overhead in running MapReduce is lot, right? They have to set up the whole thing, it has to talk to job tracker or nowadays yarn, it has to say everything, and by that time maybe you have a new batch of data coming. Right? The overhead of running MapReduce itself is high. So people have done this before, even before when there was a streaming application on top of Hadoop. It is not a nice experience. Yeah, it's a very slow. It's not really real time. It's like you can run like a hourly or kind of.
Is this flow you mean?
Sorry?
Is this flow what you mean by for on Hadoop?
No. So this is running on MapReduce itself. You can dump the data into HDFS and make MapReduce running for every some kind of cron job, right? Every few seconds. Then it kind of gives you a feeling of running as fast as possible. And even people kind of ask, what if we have unlimited cluster, right? So MapReduce can go as fast as possible. But what happens is that after some point of time, as you have more nodes, the overhead becomes so high, then there is no meaning of adding more nodes at all. Right? So then that's not a nice thing. Okay. Now, people who are done streaming on Hadoop, it is not about MapReduce. There is another framework which came along in I think around 2011, next, which did the streaming on it. Now there is a disclaimer here. I never worked on Apache Storm before. So when I heard about Apache Storm, this is around I think 2011 and 2012. At that point of time, I was trying to wrap my mind around MapReduce itself. So I didn't know what is MapReduce itself. So I did okay, Storm looks nice, but we don't need it now. So I never had a chance to work with the Storm. And by time when I say I want to do streaming, there was Spark streaming. Right? So there was so whatever I'm going to tell about Storm may not be 100% correct. That's why there is one link in the references which compare Storm versus Spark. But I want to give you like what is the idea between Storm and Spark and how they differ. Now, thing about Apache Storm is, it is a stream processing system built on top of HDFS. Now, I don't say Hadoop. The reason is that normally when the people say Hadoop, they think Hadoop is MapReduce and HDFS. So Storm do not use the MapReduce part of it again because it is slow. Now, what Storm people did is they created their own runtime which can do the stream processing. So the idea is that HDFS is nice enough to do the ultimate storage or maybe a fault tolerance, but itself MapReduce is not for good for processing. What they have done is they came up with their own way of doing stream processing. Now, the second thing is that Storm has its own APIs. They are not same as whatever the MapReduce APIs you have seen in the normal batch processing system. And yeah, they don't use the MapReduce. Now, one of the difference between Spark SQL, again Spark Streaming will come a little bit late. Apache Storm in the code is a one message at a time kind of idea, which means when you get the data, you immediately do processing and do something with it. And they also have this idea of micro batch. Their idea is that you wait for some time, collect the data, and then do processing. So normally people have this differentiation. We say real time and near real time. So that's kind of the thing people use in business. So real time means whenever there is a message, you do something. Near real time means you wait for some messages to collect, then you do something. So that's a differentiation. And to give you a kind of a little bit, go ahead. Micro batch is what Spark Streaming does. So that's the biggest difference. Now you can say, does it really make difference? May not be in most of the cases, but some cases you really want to do it immediately. May not be even that thing. It is built by Twitter. Now, I think if the history is correct, I think someone built it and then maybe he moved into a Twitter or something. So, but ultimately it is part of Twitter and it's not a surprise because they are the ones who really need this kind of systems. Right? So Apache Storm is an option to do stream processing on top of Hadoop. Now you can say, okay, everything is fine, then why you need something new? Like Storm is there, everything is there. Yeah.
Sorry to interrupt, can you go back?
Yeah, one sec.
So the first point is not entirely correct that it is built on top of HDFS.
Okay.
It doesn't require any HDFS.
Okay, it does not need HDFS, so it can be self-sufficient.
Any HDFS and it doesn't use anything from Hadoop. You can literally run it in your local box without ever installing Hadoop or anything.
Okay, yeah. So I think he worked on the, so I was just talking to him, so he worked on the Storm before. So what he says is that it doesn't even need HDFS. So which means, I don't know, is it really running on Hadoop? What it's using? Nothing.
No. See, there is a very different notions that it has connectors.
Okay.
To which it can connect. Let's say you want to have a backend store as Cassandra.
Okay.
You can have Cassandra as backend store.
Okay.
Most of them have Cassandra as backend store.
Okay.
Or you can have anything. You can have Postgres. You can have MySQL. You can have.
So it do not need a Hadoop cluster to be there. It can work
You can have
independently.
11 DB as backend store.
Okay, so that's
If
great.
it is distributable, it has Berkeley DB also as backend store.
Okay.
So it really doesn't require any of these things. And to be very sure that Storm was built by one of the famous guys who came up with this Lambda architecture. His name is Nathan Mars.
Yeah.
He used to work for another company, Packtime, and he finally got acquired by Twitter. Now he is in production. He used that for a long time. Storm.
Okay. Yeah. So thank you. So as I told, I am very little to know. So thank you for.
I just have
yeah,
a question
sure.
in this context.
Yeah.
So whether Apache Storm, are we getting that horizontal scaling advantage? Can we get that leverage of horizontal scaling with
Yes,
Apache?
it is purely distributed system built for streaming. It has one abstractions over streams. This is one of the fundamental things in streaming is that you have streams and you need to have abstractions. It is set of operators like something that you can do with the stream data or with the batch or micro batch data. So it has got very nice abstractions of what are known as boards and of course it is not Spark and Storm.
Yeah.
They have got very nice abstractions to handle the data on its stream.
Okay.
They have import and then there are phasers. They
Yeah.
have functions like transforms and multiple things. And then there is a state that you need to manage. The state is managed by some backend stores, which can be literally, it can be memory store, it can be PDB, it can be Cassandra.
Okay. Yeah. So which means Storm is a distributed stream processing system which can connect to any kind of packet. Ultimately.
It
Any
basically
store.
needs a distributed data store.
Okay. So I think that kind
And
of
one of
gives.
the points in streaming is that when you have a streaming framework, you basically need some kind of capability to look into the streaming framework and to get what exactly is the state at that system. Very simple thing is that let's say you are computing trending, there are two ways to really get the data out of a trending system or Twitter or something like that. One is you go and query the system and periodically it goes like 5 minutes and get me the top K, whatever trending items. But the second thing, or one of the facilities that it really provides, is just directly write it to a store and then combine the data from the store and what is there in memory and then get the data out of it. Storm provides even all those things. I think Spark Streaming also.
Yeah. Okay, so that kind of gives you an idea, right? Okay, let us see. I think some limitation may be wrong here. Let us see what thing I'm saying. Okay, so of course MR is not for streaming. Everyone kind of understands it. Now, one of the things, what is the selling point of Apache's Spark streaming versus Storm is, this is what we are going to differentiate. It's not just about performance alone, but this about Apache Storm needs you to learn new APIs and new paradigms. For example, you're saying bolts, transforms, which are not commonplace in MapReduce way of doing things. So which means if you are already doing MapReduce and if you want to move into Storm, it is a little bit new learnings, right? That may take time for people to get up and go through it. And also, here it says no way, but I can say here is that it is not so easy way to combine the results from what you have done with the batch with the streaming data. So this is one of the requirements we are talking about real-time analytics, right? Where we already calculate something maybe over a hourly or maybe a daily batch, then we have some calculated data. I want to combine with the stream. And there is no nice way, as you were saying, maybe we can put it in a storage like a persistent storage, then combine the stream and give it to it. But it's not directly there. It's not like you can take from a same abstraction from Hadoop and combine with the Storm also. So since Storm is different from the MapReduce altogether, combining them is not natural. So we have to have something different in order to combine. And finally, maintaining two runtimes is normally hard because now we have two runtimes. One is its own distribution system for Storm, and there is another distribution system running for batch processing. And maintaining the both stacks and making sure that everything is in sync is always hard. So the biggest selling point of Spark streaming is that it brings everything together rather than having multiple things. So what is the thing people felt on Hadoop is that, particularly the Storm, is that it is great for its own thing, but if you want to combine with any other ecosystem projects, it becomes more and more challenging. And even when we are going to look at the Spark SQL, we are going to also see we can do run SQL on streaming and those kind of things, which means they really come to. Now, this brings us to the idea which we talked long before this, unification. Right? So the Spark talks about this idea that there should be a one platform for all the kind of processing. I think this one we saw long back, where we say there should not be different runtimes for doing batch processing, stream processing, and those kind of things. There should be one, and there's a lot of advantages. So what I'm trying to say is that Apache Spark is one runtime on which you can run. We already seen the batch processing. You can run the stream processing, and also in the future meetups you will see you can also run interactive things. So there is no multiple runtimes. You can do everything on the same thing. So this is the biggest selling point of Spark streaming versus any other system, because if you already know Spark, the batch API, you can easily move to the streaming API. It is actually very easy. We'll see in the future, like in the slides, like how easy it is. So that is kind of thing, unification, right? Everything in the same place rather than having multiple things. Are you able to follow? Like what exactly we are getting into? Which means we want real-time analytics, but we don't want to use a different system altogether because there is a learning curve, also there is a maintenance work. What we want to do is that we already know Spark, we want to leverage that information and also the resources in order to run the stream processing. Now, what exactly Spark streaming is? Spark streaming is an extension of the core Spark API. The reason I have put it here is that Spark streaming do not need any new runtime. It's the same runtime what you use for your batch processing. It's just a new API which is built on top of Spark API itself. So you can think like a library. It's like a library. It's not a framework. It's kind of a library which is built on top of the Spark API itself, which allows you to do lot of fault tolerant stream processing systems. So that's kind of idea. If you already have Spark, it is kind of a library which is on top of Spark API, which we already seen before, which can allow you to do stream processing. So that's kind of Spark streaming. It's kind of a, we say in the Hadoop ecosystem project. It's a kind of another project which can do these things. Now, what Spark streaming can do, on the left you have a lot of data coming from streams. If you see the stream, Kafka, maybe you have heard Kafka, Flume, even HDFS can be a stream, we will talk about that. Kinesis, Twitter, which means you can have a lot of data coming, as I told, multiple data sources. You can do processing in the real time. Then again, we can push it to HDFS, we can push it to databases, even some places we can directly push it to dashboard kind of systems, where it can be streamed to the dashboards and it can show the other things. So it has both ability to collect the data from the different system as an input, it can do the processing, then it can push processing or output to the downstream systems. Are you able to follow what we are trying to get at here? Yeah. Any questions? Okay. Now you can say, wait a minute. Spark was a batch processing system, right? How come it suddenly became a stream processing system? Right? How come the runtime suddenly improved to a stream processing system? Actually, there's a caveat to it. There is something like what is really real time means, right? So there is a different meaning to it. What I can say is, so that's the idea of microbatch. Spark streaming in the reality is a very fast batch processing. It is so fast that you don't even know that it ran in batch processing. So that is kind of an idea. So which means in the reality, Spark never had any streaming component or real-time component. But the batch processing system is so fast. Now why so fast? For two reasons. One is that it keeps the data in memory so that those disks are gone. The second thing is that the way they do the launch of the job and run it is so fast you don't even know it. So in the reality, Spark itself is not a real-time application. What they do is that they are in a very fast batch processing system where you get a feeling of real-time analysis. Yeah.
Has anybody tried the performance of the microbatch?
Sorry?
Have you tried, when you say microbatch?
Yeah.
Have you tried 1 second, 2 seconds? Has anybody tried that?
Yeah, so we do have a streams with the different batch sizes. We can talk about it. So you're saying how much time it takes to...
No, sir, let's say I do a 1 second
Yeah.
batch, right? Is it efficient?
Yeah, so I will talk about it. I will talk about it as we go along. Right. So again, now the idea of micro batch is Spark streaming collects the stream data into small batches and then runs the batch processing on that. So you can say that you collect the data for let us say 5 seconds and whatever the data you get, you run a batch processing on it. So that's what we call micro batch, which is not like whenever there's a new data from the stream, you do the processing. It's like you wait for some time, then you do the batch processing. Are you able to follow? That's what we call it a micro batch. Now, the interesting part about it is that Hadoop batch is normally, if you do in a MapReduce, that batch has to be around like 15 to 20 minutes. Otherwise, you cannot run the MapReduce so fast to get the result. But the interesting part about Spark streaming is that batch can be even 1 second. You can collect the data in 1 second, and before the new batch comes, you can calculate the result and push it to the downstream systems. So which means you literally can collect the data for each second, do the processing, and next second you are another batch is ready. So just to answer the earlier question, right? So yeah, it is possible. Even if you say 1 second, and if you have enough data coming, let us say some megabytes of data coming with clusters like Mesos and those kind of things, you can do the processing within those batches in order to be ready for next batch. So we have been in a lot of places, even in the production, we have like 1 second batches where you can run on things. There are some ways to set up the system like Mesos system, but we can. Right? Now, one of the way why Spark streaming came along is one of the person kind of I know like there is like a history saying that some person told Spark is so fast that can we really do streaming on top? So this is how it started. So when you say in the batch processing, even if you run in IntelliJ or something, you can see that Spark is so fast, even launching a job and running it, people started to think, okay, then it's not a big deal, right? You can collect the data in batch and run on it. So that's how the Spark streaming project started. Because they understood that the batch processing API itself is fast enough to do these kind of things. Again, of course, for that time they have optimized for doing these things, but that's how it started. Which means when the Spark came along, if you see the Spark, line, it says it's a general, fast, scalable, distributed processing. Which means that fast part is there from beginning. So what they looked at is that, yeah.
Actually, if you can send us some statistics in 1 second, and this was the amount of data, 1 TB of data, and this.
Yeah, so those status I will give you in the wiki one of the things. Actually, in the wiki they have put out, all the benchmarks are there. I think they have compared with the other systems and saying how we are comparing with the micro batch processors, those kind of things. Those statistics are there. Yeah.
The processing time dictates the batch size.
Sorry? Yeah, normally we keep the batch size such a way that before the next batch comes, we have to be done with it. Because here what happens is that till that batch is done, the data will be collected, but it will be not triggering the kind of processing for the next batch. So we have to be done with that batch. Even if you are a little bit late, that should be fine. But if you are taking too much time, then those batch will be queue up for a long time. So how much time it will require for the one batch to complete normally says how much is the batch time. or for what interval you want to do. So does that answer the question? Yeah.
One more question.
Yeah.
Let's say I keep an interval of 1 second.
Yeah.
And I have some set of memory and that gets full.
Yeah.
But still incoming data is there.
Yeah.
So
Okay, so that's the question. Maybe we'll answer a little bit later. So if you don't ask for it, normally Spark only keeps the one batch at a time in the memory. Once the batch completed, it actually removes from the memory and next batch can do. And normally when we set up the memory or maybe the cluster, we kind of make sure that it can store maybe 10x or 20x batch data. So that we don't, because normally when you do any processing, it may need a temporary storage to do some processing. So you don't want the actual input to get lost. But so that's kind of the way we do the clusters. But no, if you don't ask for it, if you are not keeping any state, we'll talk about that later. Once the processing is done, that data will be removed from the memory. If you want, you can keep it in the storage, but you can just remove also. So, any other questions? Okay. Right. So Spark job creation and execution is overhead so low with because of variety of technical details. It can do everything under a second. And these batches internally are called as DStreams. Now, when we talked about batch API, I told there is only one abstraction to remember called RDD. In Spark streams, you have to only remember one thing. We call it as a DStreams. Okay. So what Spark streaming is, it's a fast batch processing system. So that's all. So that's why we have this idea of micro batches, and this is where Storm and Spark streaming differs. So Storm, in the sense, it's really a real time because it will do the processing for each message. But in Spark streaming, we say collect the data for whatever the small interval it is, then we'll do the actual processing. Make sense? Alright, let's move on. Now, what is a DStream? DStream, by name itself says, it's a discretized stream. What it really does is, you have an input stream where the data is coming, which is fed to Spark streaming. Then it will slice into small batches. So that's called as a discretized streams. Called batch at T1 means till T1 we have collected this amount of data. T2 means from T1 to T2 this is the batch. From T3 this is the batch. So internally what Spark does is that it takes the stream and divides into these smaller batches. And if you see these batches, you may be saying, okay, does it look like some partitions or those kind of things? It looks like we are back to our known world of doing the division of data into multiple pieces. Yeah, of course, so we will get into that. But idea here is that this is the thing. It is not going to immediately do any processing. It takes the stream, collects it for that point of time, and creates the small batches of it. And this abstraction is called as a DStream. So why it's a discretized stream? Because it's slicing the stream into multiple small pieces. Okay, let's move on. Now, what is a DStream? Discretized stream. Each batch's data is converted into small discrete batches. Okay, batch size can be multiples of seconds. You can have 1 second, 1 minute, or whatever the time you want. And DStream can be constructed from where it can take the data. You can take the data from sockets, Kafka, HDFS, and you can write your own receiver if you want. If you have an internal system sitting around which can emit the data, you can write the receiver and connect to it. So we are not going to cover all those things today because we don't have so much time. But literally any stream, if you have around, you can connect to it. And a lot of third-party things are there. Twitter has a Spark streaming client. AWS has those kind of things. So you can use any streaming thing and you can connect it. Now, the final thing we want to know is that where the RDD is coming. Because once we are no RDD, then everything we know. Now, what I want to tell you is that in Spark streaming, every batch is an RDD. Okay, so that's all. So then how the processing is done, you already know. So that's why I was telling you last time, I need only half an hour for Spark streaming. Because once I say RDD, people say, oh, we already know RDD, we know map, flat map, everything is there. Exactly. So why it is like this? Because already Spark runtime knows how to do processing of RDD. And if you give RDD to it, it knows how to do the processing. So what they do is that they take the stream, they slice it into multiple batches, and each of these batches internally stored and represented as an RDD. And this RDD is fed into the stream runtime in order to do any active process. Are you able to follow what I am trying to say? Which means internally it's the same API as batch API. It's just the abstraction layer where it's saying collect the data, slice it into multiple pieces, then give that piece as an RDD to you, then you can do any process.
So what it increases the resource management because there could be so many batches.
Yeah.
We are creating so many RDDs.
Correct.
And that
so it will occupy more resource.
Yeah, so that's a good question. So the question is, what if you have so many batches and if you have keeping so many RDD? As of now, I have not told you where RDDs are kept. By default, RDDs are kept on memory, and the default policy is that once the batch is done, those RDDs are flushed out. Because these are RDDs, and by definition we know it's immutable, which means once the batch is done, those RDDs cannot change anymore. And once the batch is done, you already know that you have done the processing for that RDD, then it is free to flush. So every few batches, the RDDs are flushed out, only new RDDs will be kept out. Okay, any other questions? All are happy to see the RDD in place again? Because we know the RDDs, right?
DStream is like a wrapper around RDD.
Yeah, DStream is actually a wrapper around the RDD. Okay. Now, each batch of DStream is represented as RDD. Now, one nice thing about RDDs are they are fault tolerant. Because when you are doing streaming, you don't have this data in persistent storage. So, this is the one part you have to remember. When we do batch processing, we already have data in HDFS or some storage. Even if we have some problem with whatever the processing we have, we are okay. We can rerun and we get the same result. But when we are doing the streaming, if you lose the data, you lost forever. Right? So you need to have a fault tolerance in such a way that even your processing goes down, you can take the data and dump it somewhere. So since Spark RDDs are fault tolerant by nature, if you represent your streaming data as an RDD, they can be replicated over a cluster in memory, where even if something goes wrong with the processing, they can be dumped into the disk. So because in RDD there is a way to say storage, memory and disk. I can say keep it in memory, but as a fallback also put it in disk. And if you are using tachyon and those kind of things, you can say use a tachyon and it will do all the fault tolerance for you. So, but idea here is that it is represented as RDD, so I get the fault tolerance for free. I don't need to do any fault tolerance as separate thing for streaming. You get the data, it is replicated over a cluster. Again, you can configure how many machines and those kind of things. Once you get it, then you are good to go. Okay? Now, the nice thing is that every DStream operation ultimately results in RDD transformation. So whatever you do in the DStream ultimately will be run on RDD only. Then what happens is that there are even APIs to directly talk to RDD. You say, I don't care about DStream, I know there is RDD lines somewhere in behind you, give me the RDD itself. So you can even, we will see one of the example, we can say, give me the RDD, I will do some interactions. Which means I can say, I skip the whole your streaming API, I don't care about it, I know the batch API, give me the RDD, I will be fine with it. So even you can do that. Now, the nice thing is that, since both streaming and the batch talk RDDs, now you can combine them easily. Right? Because if you read the data from file, it is an RDD. If you read the data from stream, it's an RDD. Since both have same data structures, now easily you can combine them. Which is not true with the HDFS kind of Storm kind of things, where they have different things. Now since both talk RDD language, now you can easily combine which is coming from batch or which is coming from stream and give the better results. So this is the strength of Spark, where everyone talking in the same language called RDD, and then you can move between the streaming, batch processing, or even interactive things where everything will be translated naturally, rather than you have to write a wrapper. Yeah.
From batch we create one RDD,
Yeah.
and then we do transformation on that RDD.
Yeah.
Again, we have to create one more RDD for that transformation.
It will create itself, you don't have to do it yet. So each transformation results in a new RDD, but everything will be managed by the Spark itself. So you just keep on doing that.
This will increase the space, right?
Okay, so I think we already talked about laziness, which means really nothing happens till you really ask for it. So all the transformations will be combined to give you a final RDD where everything is combined. Not every transformation results in an actual physical RDD. So all the laziness, everything is given there in the DStream. Yes. Okay. Now what I wanted to show you the next is this one. You don't need to learn new API. That's so simple. If you already know batch API, that's the API you are going to use to stream. Why? Because if you see the first two lines are different. The first line is a new context and there is a way to read from the socket. But after that, do you see this flat map? You can do flat map, map, reduce by key, join by thing. Whatever you've done already in the batch, you can do. The reason is that internally this is how it works. You get a batch, you get an RDD, and you say you do a flat map on batch. Internally it is done a flat map on RDD, then you get a flat map. That's all. That's why batch API and the stream API are exactly same. Which means you don't have to learn new API. There are a few new APIs are given for streaming, like there is something called window, but internally they are mapped back to the RDD APIs. Are you able to follow what we are trying to get at here? This is called unification, which means all the different systems in the runtime going to talk the same abstraction, so that I can learn one API and I can reuse in all the places. So this is what makes Spark streaming very attractive, because if people already know Spark and working in the batch processing, I can literally take those batch API code and move it to the streaming. So recently I was working with one of the company where they were running a 1 hour batch on their data from S3. Now they can take the actual same code and run it on the stream, because both talk the same RDD abstraction. Once I get hold of the RDD, I can run the same. Again, there will be some different performance characteristics, but other than that, the way we do the work or the way we express the different transformation, they will be exactly same in the batch API and they will be exactly same in the thing. Now, you may be now thinking, okay, what happens to these partitions, what are the things we talked about in anatomy of RDD? I will not go deep into this, because there will be we are planning one session some point of time, a deep dive into how these RDDs are represented. But as of now, we think that, okay, these are normal RDDs. Whatever you can do with the batch API, you can do with the this one also. I think maybe run out of power. Okay, give me 1 second. And also people may be thinking, where is the break? Actually, there is no break as of now, because there is another session. Last time I had only one session, so I can take any amount of time, because there is another session. We are going to go complete this, maybe take a break, and then we'll come back to the. And also, yeah, there's one more thing I want to tell. Today there is a pizza, right? So people has to be here, take a pizza and then go, right? So we have time. Okay, so there is one more announcement before our system is back. I think APH is hosting another meetup. I think World Map or something. If you are someone is came here, we are running Spark here. So it is in HSR level. It's in HSR level. I'm not sure if anyone is here who is supposed to attend non-Spark. Please go to HSR. Maybe too late, but the same. Okay. So what I want to show is that all the APIs are same, which means we can easily interact with the stream as we interacted with the batch before. So yeah.
Once we the batch at T1, that's
Yeah.
a DStream object.
Yeah. So this batch at T1 is a DStream.
So once we do a transformation like that,
Yeah. So what we get back is DStream, which is wrapped around this RDD.
so every transformation you give me a DStream.
DStream back, correct.
Inside it's an RDD.
So the question was, when we do a transformation on DStream, do we get back an RDD or a DStream? You get back a DStream which is wrapped around the RDD, and there's an API we are going to see which you can directly take an RDD and work with it if you don't want to work with the DStream. The reason is that DStream APIs are limited. There are only few APIs which you have in the batch. If you ask for more, they will say you have access to RDD, go and use it. So I was talking to one of the guy in the Spark stream. They were saying we are not going to add more APIs because you have access to RDD, and if there's an API, you can use it. That's the kind of thing. Okay, next. Now, so from now on, we'll do some hands-on. So till now we have understood why we need, what we need, all those kind of things. From now on, we'll do some socket stream, we'll do some word counts, we'll see a few of the things just to get a feel. And you may be screaming inside your heart and saying, I know these things, of course, because all the RDD thing what we have done before. But let us see how we can run this example and see what we get out of it. Okay, so first thing we have to see is the socket stream, because we already worked with the files before and files are boring. Right, so let us have something actually which is streaming across and you can do some processing on it. So that's the overall idea. So socket stream is you can listen to any socket on any remote machine. You can say which is the host and which is the port. Now socket stream has both raw and text representations. You can say give me the raw bytes, I will make a sense out of it. or you can ask for a text representation. We are using a text representation for our example, but you are not limited by the text. And nice thing about the socket stream or any of these streams is they have this built-in retry mechanism, which means let us say your application went down for some time and it came back, or sorry, I mean the socket went down for some time and it came back. Actually your program can retry for some time and keep on listening and see does the socket came back. You don't have to restart the program yourself in order to connect once the source is restarted or something. So it is the retry mechanism is built in inside the socket stream where it can repeatedly try to connect. Once it comes back, you will be good to go from there. Okay, so that's what we want to see. Okay, so next one is example. Now, how many of you are running IntelliJ? Okay, few of you. How many of you are running Eclipse? Okay, so I am not really sure that can you run from the Eclipse because I have looked at Scala ID and I said, okay, I don't understand what's going on here. So the third option we have this time is command line. So that's the savior, right? You can do anything in the command line. So what we do is that we are going to run from the IntelliJ once, so that people who do have IntelliJ can use it. We are going to run from command line. And if someone figured out how to run from Eclipse, I encourage you to come here and show it for people that how to run from Eclipse. So that's kind of a status we are in. And also in IntelliJ I have found out that there is something called presentation mode, which is good for videos. Right? Let us go to the IntelliJ. And also I am going to only run 2 examples maybe because then we can save time and I will explain the other examples. Anyway, you have a code with you, right? Okay, we are in presentation mode. I think we are not in the wrong example. Let us say Alt1. Let us go to word count. So we like word count. Okay, just Alt1 again. So that will be Alt1. Okay, everyone is able to see the code, right? Okay, so I have to explain only 2 lines. The first line is, there is a new context called streaming context which has this DStream idea. I think you have seen Spark context before. You can construct a streaming context from Spark context also, or you can create a new streaming context from yourself. The first part it takes is your master. We use a local host. Now only there is one small difference, I will talk about it. Next one is the name of your thing. This is the batch size. Here I am saying 20 seconds means for every 20 seconds create a new batch. The reason I have not kept 1 second is that it is too fast. So 20 seconds just gives a time what's going on here. Then the next one is rather than saying text files, now we say socket text stream. Saying that don't take from the file now, take it from the stream. So stream this socket text stream takes 2 parameters. It takes which host name it is listening on, which is the port, which is too straightforward. And then after this is all we know. So we take the lines, we do flat map, we do map, we do reduce by key to do the word count. This is exactly same as what we have done with the RDDs. So this logic do not change. Finally, the way we print it a little bit different. We don't say collect, we say dot print. Then these are the 2 new lines, start and avoid termination. Now the difference between a batch program and the streaming program is, batch program is something we submit after we have the data and it runs and it completes. Make sense? But in the streaming, it's always listening mode, which means it keeps on listening to the socket, and once the data is there, it does the program. It never ever completes. So that's why these 2 lines starts and it says await termination means keep on running till I ask for it. Till I say stop, you have to keep on running. So this is the difference between your normal batch and your streaming. In the streaming, I have to say get the data from the stream, do this transformation, show the result, and get back to the loop. Keep on listening. Whenever there is new data, do something. Which is different in batch. In batch, we submit the thing, it runs over the some time, completes, you get back the result. This is a little bit different than what we have done. Make sense? Now, there are 2 steps here. First, we have to have a socket which can emit the data. The second, we will run this example. Because when you run this example, it will ask for the stream. If the stream is not there, it will start throwing error, saying that, okay, I don't see the stream to connect. So these are the 2 steps. And what we'll do is, first we'll go to command line. Right? Okay. So open the command line. Maybe you have to zoom a little bit just to see like what's going on here. Okay. Yeah, show menu bar. Show menu. Okay, so our control, yeah, zoom in. Yeah, control plus. Alright. Now, people who are on Windows, how many of you are on Windows? I'm hoping that you installed Netcat. Okay, great. So, if you are in Linux, you can write NC. If you are in Windows, you say Netcat. So, we say NC space -L space localhost and space 50050. Okay, just click on that laptop battery is critically low. Okay, now this port is random, you can choose anything you want. I am just choosing 50050. Here what I am saying is that NC stands for net cat. So I think everyone knows cat, where you can say cat and put the data in STD in. This is for network. And if you are in Windows, I had this issue with the local host. Replace the local host with the IP address. Whatever the IP address you have. Okay, how to get IP address is IP config. Right? You get the address. Here I am saying read from the input stream STD in and put it to the network. So that's what I am trying to say to NC. Now nothing is coming here. The reason is we have to input something, but let it be here. Let us go to IntelliJ. Okay, say let us run this program. I think we have to give some parameters. Okay, I think we'll get an error, or maybe it's already filled up. See, go to top and see. Maybe you have to exit the run the edit configuration. Applications. Yeah. So these are the parameters you have to pass. Now the one thing we have said is that when we run in local, we give local. Now only for streaming, very specifically, you have to give local of 2 or more than that. The reason is that always you need 2 threads, 1 thread for getting the data, 1 thread for actual processing. If you just say local, you only collect the data, you never process it. This is even in the documentation they specifically say you have to say local of 2 at least. That's why we are saying local of 2. That is our master URL. This one is saying localhost is this where our socket is running. This is the port where we are running. I think port is wrong. We say 50050. Okay, so these are the 3 parameters, and I think with the zoom in you can see even in the video, right? What is the parameters? So people have parameters for. So local of 2, localhost and 50050, and say OK, and let us run it. We may have errors. Not this one. Says cell record parser is not there. Okay, just go top. Okay, just delete this file. So we don't need example. Yeah, recoverable cache. Yeah, .com. So let us run the .com. So I kept one example, just say making that if I am going to complete faster, then we can run, but that's not going to be the case. So let us run it. So are able to start the socket. Then after starting socket, run this thing. I will show you how to do in command line also. I think it's there in GitHub, but if you can wait for that. Anyway, let's give some time for Scala to compile. Okay, we are running. Just make it big so that people can see what's coming on. Okay, just go. Okay, so it keeps on saying it was listening to things. So what it does is that it says for this time nothing is there. So it keeps on printing this thing saying that what time we are. Now let us do something interesting. We have to give some data to the program, right? Let us go to the command line. Let us type something. Say hello, how are you? That's our normal thing. And say new line. Okay, just let us go back to our program. Let me have say, if you see here, it says added input 00 something, which means it has collected the data. Let us wait for 20 seconds, right? Our batch size is 20 seconds, and it will show you some. I think it should count and tell you that something is there. Maybe 20 seconds is a bit more for talk. Yeah, okay. Can you see this? You are able to calculate the. So here idea is that you open a stream, you connect your program, it keeps on running, and whenever there is a data, it collects it and keeps it. And after your batch time is done, you can run the actual process. Are you able to follow? And I'm not going to wait for you guys to run. The reason is that the time. So what you want? We will continue about the discussion. And if you have any issue with the running, anyway, we have lunch today here itself, so you can discuss with me and we can fix it. Is that fine with everyone? Okay, code is there, everything is there, and I'm here always, so don't worry. Now let us move on. What do you want to see next? So let us go to the slide. We will stop this. No, let us stop the IntelliJ. Otherwise it will take a lot of things. Let us go to the slides. Okay. Now, word count is simple. So I am not going to focus on the API unless there is a difference between batch or stream. Okay, because you already know the logic. I'm only going to focus on the stream part of the equation. Now, you can say I don't have any socket coming in because I was doing batch processing till this today. I don't have any socket, but I do have a S3 bucket or maybe HDFS folder where I keep on putting a file for every hour. Maybe your log files you are putting and those kind of things. Can I do some streaming on top? Or you can even say, I was putting 1 hour because I am going to run for 1 hour. Can I put every file for 5 minutes and run something on top? Which means that's how you move from batch processing to stream. You not say, okay, open a socket and let's stream it. No. What you do, you stay from 1 hour window and say, can I put a file for 5 minutes? Let that stream pick it up and do some processing. So that's where the file stream comes to place. Now, what the file stream is that you can monitor a HDFS or any kind of file system where you can look for a new files, and whenever there is a new file, that is recognized as a stream. So what we are doing here is that we are making a stream out of a file system. And this is very useful if you are moving from a existing batch to the streaming thing, because these do not need any changes from the infrastructure level, because all the files are already there in some place. Now you can say, take this as a stream and run with it. Now what happens is that whenever there is a new file appears, Spark streaming picks it up. And once the batch time is done, then the actual processing will be done. So as you see from the socket, now you can do from the files also. Now you can say how Spark is intelligent, how it knows there is a new data. Very, very clear. It has to be a new file. Update to the existing file will be not picked up. So if you are doing a same file with the new data, the Spark streaming will not pick up. Very simple implementation. It always goes with the file creation time. If the file creation time is greater than your actual starting processing, that's the starting time of your processing, then it will pick it up. Anything before it, it will not pick it up. And I have seen some strange places where it can pick up modification date also sometimes, but it's always good to go saying it's always a creation time. If there is a new file with a new creation time, it will pick it up for you. If you do existing updates, you cannot do really in the HDFS, you can only do append, but even the appends are not recognized. So what you can do is that, take the file system, any file system, HDFS or anything, open a stream to it, then whenever there is a new file, then it will become your Spark streaming application. So as you have a socket stream, you can have the file streams. So I will just show you an example. We will not run it, just show you the API part of it. Let us go to the code. Say white one. Just make it small. Just go to the file stream. Just say white one. White one. Okay, straight. Okay, anyway. So rather than saying socket stream, now you can say text file stream. You can say args1. It only takes the path from where I have to pick up, and all the logic remains same. If you see the first line and after that line, everything remains same. So only the DStream, how you construct differs. All the logic, how you process, everything remains. Are you able to follow? You can have a talk to a socket. So the reason why I saw a socket is that's the real stream. But if you already have a file system which is collecting the data, you can open a file stream into it, and whenever there's a new file, you can run the streaming on it.
Can it remotely connect and
Sorry?
can that file be existing in a remote HDFS?
Yeah, it can talk to HDFS, any FS API.
Remote machine.
Yeah, even
Spark
remote.
can be in a different.
Yeah, it can be. It can talk to remote other clusters also.
Another doubt is
Yeah.
you said we have two threads. One is the collecting thread and another
Yeah.
is the processing thread. So if you see the first two lines is the collecting logic, right?
No. So when this program runs, there is always collection phase. And once the collection is done, there is always running phase. So it's not just, this code is just saying whenever there is a new batch, what I have to do it. Actually, this code will be changed into something we call as a stream graph. In the graph, there is one stream coming in, there is a processing pattern. So this is a way to say what you have to do when there is a new batch coming. So these new lines will not actually execute. What I am saying two threads is, one thread for this receiver to keep on collecting the data. Once it collected the data, it will store. We'll have architecture after this. Then one thread to actually to do all the Spark transformation. So these are the two threads. When you do in the cluster, actually there are two machines. One machine running the receiver or the collection of the data. One machine actually running that processing. So this code is not exactly the code, it will get transformed into something called graph, where there will be this hook sign input stream, and for every batch part to be done. Okay. Okay, are you able to follow? I think the samples are easy to write because we already have the logic. Yeah.
File format.
Sorry?
File format.
Not able to follow.
File format, how do you specify?
Oh, so good question. So how do you specify the file format? Actually, if you see this text file stream, internally it's a text input format. Okay, so similarly, I think they do have, I'm not sure, do they have a built-in, but you can write a custom receiver where you can say this is the input format, take it from HTML. So this text file stream internally is a wrapper around input format of the Hadoop, the file system. So there you can specify what is the thing. So if you have a different delimiter, there is one option to give here only. But if you have a binary format or any other format, I think there is even the JSON stream, those kind of things built in, but you can write your own if there is no. Okay, all are able to follow? So the idea is that logic is same. The way we construct the DStream, which is underneath the RDD, is different than what we have done with the batch API. So that is the strength, which means these 3 lines I can literally take and copy paste in the batch API and it works if the line is a text RDD. So it's like a copy paste aware API, right? Exactly same API. So this is not similar API, it's exactly same API. So they are both are same. Okay. Now let us move on. So I have 3 more examples to do, right? So file stream we already saw. Now this is the architecture when you really run it on a cluster. So the idea is that I have differentiated 2 pieces. There is this Spark cluster which is having multiple nodes. Actually the streaming application also runs in one node, but that is not needed. What is this streaming application is? This is a driver, which means which is listening on to that port or whatever is actually running that code, that JVM. Now what it does is, this thing has this transformations. Whatever the transformation you have done on the stream, they are going to be sitting in the streaming application. And if you see, the receiver is not running on the same machine. It may be running on the other place. The reason is that, as I told you, we need 2 threads for parallel things. This will be only doing the transformations. The receiver will be actually collecting the data. Actually, they are 2 different pieces. So even if this application goes down, your collection will be not affected. You can keep on collecting the data, you can restart this application, you can come back and actually start processing the actual data. So the receiver and the DStream transformation, they are be separated, and in the very large scenarios, there will be multiple receivers. For example, if you are worked with, how many of you work with Kafka and those kind of things? Heard? Okay. So in the Kafka or even in the other MQs, you have this multiple topics idea, where you can shard the input stream into multiple topics and you can consume in parallel. In that cases, you can have multiple receivers where it will be taking some part of the data, then you can combine and do the processing. So idea, why we need multiple receivers again for fault tolerance. If something goes wrong with the receiver, we don't want to lose the whole stream. We want to collect the data and go. So what I want to show is the receiver is different. Now, you can ask me where these RDDs are coming from. Right? Who is taking these RDDs from the stream and who are making it? I think last time we discussed about block manager. Right? I told you block manager is a piece which is running in both in master and slaves, which is our kind of coordinator of all the in-memory data structures. So what stream does is, in the receiver there is a method called receive, which takes from the maybe a file or maybe from the socket. It calls a method called store on the block manager. So what block manager does is, it takes the stream data and it shards across or distributes across the cluster, because block manager is built for those specific things. So what happens is that receiver takes the data, dump it to the block manager, where it actually puts into the cluster in memory. Then block manager creates something called block RDD. So what is a block RDD? It is an RDD where the partitions are sitting in memory. So it's as simple as that. So block RDD is an RDD which has its partitions, that the data sitting in the in-memory data structure, whatever the receiver is given. Then this RDD is given to the DStream transformation. This is how we construct RDDs from the streams. So receiver collects the data, gives it to the block manager puts into the cluster, then it creates an RDD out of it, then that RDD will be given to it. Then you can say who is running the job. Once the transformations are triggered, there is something called job generator. It is like, okay, I'm going too deep here, it's something called actor, which is keep on listening mode. Then it takes those transformations and runs on the Spark. So this is kind of internal architecture. So receiver takes the data, gives to the block manager. Block manager generates this block RDDs, and once you have the RDDs, you run the transformation, and actual transformation will be run by something called job generator, which actually creates Spark job for every batch. So if you see your yarn manager or any thing, you can see for every batch there will be a new application running or new batch job is running. Job generator is. Now here I have only put 4 blocks, but if you really go through the source code, there are around 50 different things, all for timing purposes. So there will be a timing for triggering the batch, there will be some timing for getting the results, there is so many other pieces for purely for timing, but these are the things you have to know, like how the things are. So if you see here, that's why these transformations are agnostic of streaming. The reason is that it only knows the RDD here. It do not know stream, or it do not know how the things are. And it also knows that these are where they are kept, it does not know. Only the block manager has this idea that it has to be in memory. Right? The DStream transformation says, okay, maybe this is coming from a file, maybe this is coming from something else. I don't care. It's an RDD, I will do transformations. So that's why they were able to use the same API and abstract it out the actual streaming part to something else. So if you say, what is Spark streaming? Yeah.
So can you see the job generator in this console? I mean, actually
no, it is an actor actually. So actor may be a thread also inside running in a JVM. So when you run in a cluster, it will be a part of, I think, some of this. So they are not different. So there's just a one piece running which is generating this data.
is the logs in what's
In the logs, I'm not sure. Does it say job generator?
run this sample, right?
Yeah.
Block manager.
Yeah, block manager it says. Does it say job generator?
No, we see a job scheduler.
Job scheduler. Okay, maybe the name is job scheduler.
Oh.
Okay, so there is 2 parts to it. Job generates the jobs. Job scheduler schedules the jobs. Okay, there are 2 pieces in it. Okay.
One question.
Yeah.
So when it gets replication for the fault tolerance, it
Yes.
takes a block RDD level or mini batch?
This block manager. So block manager has this logic of replicating. From the replication, block RDD comes. So block manager by name it says a block. It can take any block of memory or data and replicate across the cluster. So from that I can create an RDD. Yeah.
So
Sure.
you told about fault tolerance.
Yeah.
This architecture, how does it work?
Yeah, so the architecture, this block manager normally we use in the batch API for doing caching. So when we say cache, block manager takes the data and replicate across the in-memory cluster. So here, since the data is collected by the same block manager, it takes the data, replicates across the multiple machines in memory. So that gives the fault tolerance. So even if the one machine goes down, that data is there in another thing. Another part is that when we create a DStream, I can say what is the storage level. In Spark there is idea of storage level. I can say memory and disk, which means it keeps in memory and also as a fallback there is a disk part. So again, that's also coming from block manager. So that's a point.
Sorry, replication is partitioning, right?
Sorry?
The replication with block manager is by partitioning, but not by, it's not actually replication, right, in block manager.
So actually block manager replicate blocks per se, and this partition we create for RDD purposes. See, normally we go reverse. We take an RDD and tell to the block manager you do the replication, where the RDD is already partitioned into partitions and it can do a replication. But here is a reverse way. We take the data and we say you replicate it. From that replicator, for that batch, we create an RDD. So block manager in the purest sense, it can be a kind of piece of software which can take any block of data and replicate across the cluster. So it did not need to be RDD or it did not need to be, because in the block manager we use for all these broadcasts also will be used the same thing, where there is no partition and those kind of things. So block manager can take any data and replicate it. Okay, any other questions? I think this is the biggest piece. What is Spark streaming? This part. Receiver, block manager is still there in the Spark. These few pieces where they have an infrastructure to facilitate the streaming part, but actually API part still remains the batch API. So that's the nice part of it. You don't need to know this if you are programming this. You need to know if you are doing some operation and those kind of things, right? Okay. No questions? Are you able to follow? Okay. Right. Now, we are going to go to the next thing, which is very interesting. When we do stream processing, states are important. What is a state means? I want to keep something across multiple batches. So most of the transformation maybe say, okay, I'm only limited to the batch, but sometime I want to keep count, or maybe I want to keep something which is across the batches. So that's what we call stateful transformation, which means can I keep a state which is across the multiple patches? Now, in sparse streaming, you have an ability to keep any random state you want. So some of the applications or some of the frameworks, they actually specify what kind of state you can keep. It's not any random. In the sparse streaming, you can keep any kind of a state you want. Now, the state also fault tolerant. Now, this is important. Let us say you kept the state, but something gone wrong and the whole state is lost. Not really useful, right? And also, you cannot recreate the state because you already see maybe 1,000 batches, and recreating again is difficult. So, whatever the state you are keeping has to be a fault tolerant state. So, we will see how we can do it. And also, there is something called semantics in streams. Now, what is the meaning? Let us say, what is the guarantee from the streaming application to you? That's what we call semantics. So, if you are not worked with the streaming, it may be new to you. So, what we say is there is something called exactly once or at least once. So, these are like two different things. What is at least once or exactly once? Exactly once says you get one message exactly once. Whatever the data you are streamed, right? That one record, you get exactly once. What is at least once? It says, I give you a guarantee that at least you will get once. But if there is some problem, I can maybe send twice also. Make sense? Because the reason is simple. Building at least once is easier. Which means if even everything goes wrong, you can dump it somewhere and send maybe multiple times. You don't need to have this unique counter saying that I will send that before, those kind of things. Sending exactly once is difficult because someone has to keep track, are we really send the data or is it really delivered to the DAT or those kind of things. What Spark Streaming says, they have this exactly one semantics, which means we will only get once. Now you say, what is the big deal, right? At least once or exactly once. It has a very important part in the state. Let us say you are counting how many number of messages you got. That is a simple state you are keeping in the whole across the batch. Let us say what happens if there is at least once. You are over counting. Right? Maybe the same message is sent twice, then normally you start doing over counting. But when you say exactly once, you are 100% sure always that you are actually counting only once. So when you are keeping the state, or if you are working with any streaming application, make sure that you go through what is the guarantees are given by the streaming application. Is it at least once or exactly once? If it is at least once, you have to have a logic to differentiate, are we seeing this before or not? If it is exactly once, you don't have. All are able to follow? These are something which is new for streaming only, which is not there. In the file there is always exactly once. You don't get two things, right? Okay. Now, there is one more thing in exactly once. I just giving this for people who already seen. If you are not able to follow, don't worry. Now, you can say, what happens when the receiver crashes? Let us say you have a receiver which is collecting the data, it crashed. Now what happens? Do you get exactly once or at least once? Now what they do have is something called the say val, which is a write ahead log. What it does is it also keeps some file in the local file system which keep tracks of what we've seen before. So that even the receiver crashed and if even the receiver is getting duplicate data, with the write ahead log, they can make sure that you are still getting exactly once. Again, this is something new which is there in 1.2 and 1.3, but you can use those things also. Which means, what is the idea here is that I want to make sure that I get one message only once, so that I can keep a nice state which is not over counting or doing something different than what is normally supposed to. All are able to follow? So this is stateful transformations. So we'll see one example. So here, till now what we done, word count for each batch. Now we want to do word count for whole batches, right? We don't want to say after each batch we'll forget what is the data. Now, if you just come down, I want to show you only one. Till now, everyone is same. So here, all the lines are same. Now, once I calculate some result for a batch, I can call something called update state by key. Now, states are kept as a key value pair. You can keep any number of states as you like. You can say update the state by key. What it takes is a function. So what it takes is a function, and let us see the function. It says, it takes two things. It says, what are the new values you are getting and what is the old state. So what you get in the function is that, what is the old state and what are the new values you are seeing. You can combine this both to get a new state. All are able to follow whatever the function does. What function gets is, what are the new values I am looking at, what is the old state I already have, I have to update. Now if you see the signature, it is an option of something. Now the option of something means option has two values. It's a data type of Scala where some means there is some state kept. There is something called none. None means I don't have any update, or I want to drop this state from the thing because I don't care anymore. So what happens is that if you in the beginning the running count may be none because there is no running count. I have not kept anything. But once you get some more value, here you are going to compare. So what I am going to do is take the whole thing, make a sum to get me the new values. Then running count get or else 0. Here I am saying if there is a something value, get me the value. Otherwise it will be 0 for me. Then I make the new count. Now you may be saying, okay, wait a minute. Where I am doing this key and value differentiation, right? I want to count for each word, not for every line. So that's why the name itself says update state by key. These states are only updated for key, and for us the keys are words. So there is no random state per se. You have to say this is the key for my state and this is the value for my state. So that's why you can only keep the state in terms of key value pairs. This allows you to keep any number of states. Each key will differentiate what kind of state you are keeping. So all are able to follow what I am trying to say. Once you calculate something for the batch, have a function which will say, okay, with the new updates, with the new values, I want to update the state to something new. So this is the API which is not there in your RDD. So there in RDD we use accumulators, right, to have the state across the multiple transformations. In the similar idea, we here use the update state by key operation for keeping state. And most of the application where we have streaming, we are going to have states, particularly for metrics. Right. Normally we keep the state for calculating how many things we have seen, how many let us say exception we have seen, those kind of things in the state, so such a way that we can query and see at a time saying that okay, how many users we are seeing, those kind of things. So most of the streaming application we want to keep the state, and how you keep the state using something called update state. Are you able to follow? No issues? Okay, go to the slides. Now we are not going to run these examples. Okay, only one thing I wanted to show. We'll see. I think I forgot. Just come on. Okay, when you do a state operation, there is something called checkpointing. So we are not going to go deep today. What is the checkpointing? What is the checkpointing is that, so whatever the transformation, whatever the RDDs you have, right, or whatever the things you have done, these will be written into a persistent storage when you say checkpointing. So that's how the states are normally fault tolerant. So when you keep the state, they are not only kept in memory, they are also kept in HDFS, or you can say whatever the storage you want. So that even if something crashes, the state is not lost forever. Here I am saying both the cluster is crashed, let us say, all the in-memory things are gone. You can have the storage, and this is mandated. If you are doing update state by key, you have to give the checkpoints. Otherwise you will get an error saying that checkpoint is not on. So this is one thing I want to show. So such a way that if the state is lost from the in-memory, you still have it in the persistent storage, maybe in HDFS or wherever you want to dump it ultimately. All are able to follow? So this is state transformations. I'm going a little bit maybe fast. If you have any doubts, you can ask. Now the question is, if you see the state, you can say, normally state is a mutable operation. Everyone at this? Normally when we say state in the application, we mean that there is some mutation going on. But in Spark, we already talked about immutability, right? So whole Spark is built on top of this immutability idea. Now you can say, how you can handle this mutability in terms of immutability. Now, the idea here is that if you have studied any functional programming, the way we represent a mutable state is doing state transformations. So there is no really a state update. What we do is that we take a state, we apply some function, we get it to a new state. It will not change the existing state. So in your normal Java or any other program, you maybe go and update a counter or those kind of things. But in the functional programming or immutability world, we don't change the existing things. We apply a function to get a new value. We keep the old value as it is. Okay, so that is the semantics that we are using. That's why that update function looks like that. It gets the older value, it gets the new values, combines it to give a new state rather than saying, okay, go and update in the existing state. Are you able to follow? So it is not a mutable, it is immutable. The way we handle state is apply a function to get a new state rather than having a same state updation. And of course, state is represented as an RDD underneath. So it is fault tolerant. And what we do is that we say, take a function, old state, new info, get a new state. And this will create a new RDD rather than changing the existing RDDs. So all the states, even the batches and the states are kept as an RDD, and once you have an RDD, you have an ability to do the fault tolerance. So that's why I told RDD is kind of one thing you have to remember. Everything else is same. Now, okay, so that's what we wanted to show. Okay, now this is the final thing we will do, and we'll give a 10 minutes break. Maybe I am going for long. The last part I want to show you is how we can combine the data which is sitting in the batch system with the data which is coming from the stream. Right, this is very important. That's one thing we were talked about. And the way we do it, that there is an API called transform in the DStream, which gives us the ability to directly access RDD itself. And we can take that RDD and combine with any other RDDs. So that's what we want to show. We want to create an RDD from the batch. We want to create an RDD from the stream, which is created by DStream. I want to combine them and create a new stream out of it. Are you able to follow what I am trying to say? So this is the ability to take the existing RDDs which are coming from batch APIs, take the RDD which is coming stream, combine them such a way that I can enrich the data which is coming through the stream. Now, what is the use case? For example, let us say you have an online shopping cart. Now you are getting a card information. Now you have to generate a bill in the real time, or maybe you have to give a discount. For that information, you need a customer information, correct? But customer information is not there in the stream. It is sitting somewhere in the file or maybe in the database. Now what I want to do, take the customer information from the file, take the customer cart information from the stream, combine them to say which customer is buying what. Are you able to follow what I am trying to say? Let us see how to do it. Just an example. Again, we are not really running anything. Say card customer chart. Right. Now, if you just come down here, little bit, yeah. Right. So first I am creating a streaming context. Everyone understands. Now, if you see here, this specific line, I am saying streaming context internally has Spark context. ssc.spark context, and I am saying text file. So what I am doing is there, I am creating something called customer data RDD from the batch API. So I can take the stream API, get the Spark context. Once I have the Spark context, what I can say, text file, take the data from the batch API and create an RDD which contains the customer information. All are able to follow what I am trying to say? Then, if you come down, we have a card stream which is from the network stream where I am getting all the card information. So we have two things. One RDD created from the file where it has the customer information. One more thing we are creating called the network stream where it has all the card information. Are you able to follow what I am trying to say? Then on the card stream I can set transform which gives you access to something called card RDD or the RDD which is behind the DStream. And once you have the RDD, just come down a bit, you can call join on top of those two RDDs. If you see, card RDD came from stream, customer RDD came from batch. Are you able to follow what I am trying to say? Now once you have two RDDs, naturally you can combine them, and nice part to it is transform. Once you execute this string, again will be a DStream. Okay, it's again a stream for you, which means again you can do whatever the stream processing you want. So this is the what makes Spark streaming very powerful. Ability to combine batch API with the APIs what you have already worked with the stream naturally in order to get a new streams or new RDDs and continue with it makes it very, very powerful. The reason is that both internally are RDDs. Are you able to follow what I am trying to say? This is what makes it very, very powerful. So such a way that even if you don't have a way to do it in a stream, take an RDD, have our functions and do anything with it. And last time we also see extending Spark API. Right, we can have our own APIs on RDD. Those things also work in these RDDs also. I can have an RDD which says take from the stream, run my own functions on top of it, then again get the result. So the ability to combine RDD from the batch and RDD from the stream makes it Spark streaming very, very good. Are you able to follow? So the API is we call transform. Okay, so again, I'm not going to run this thing, right? Right, okay, transform API, right, what else we have? Maybe I'm going a little bit too fast. Before I continue this, any questions? Are you able to follow or is too much for? Actually, I thought this is too less examples, but it seems to be too, maybe because a lot of people are first time streamers.
So there is a join operation there.
Yeah.
So how reliable is that join? That would depend upon your window size here, right?
You mean how much time it takes to do the join and do the things? Okay, so yeah, that you have to plan it in the infrastructure. Of course, so join may take more time in order to really do the whole join and next batch. Yeah, that you have to do it in infrastructure.
Or maybe you have to make sure that the data is sorted so that you don't.
Yeah, one more thing is that whatever the customer RDD we see, we can cache it in memory. So we can say customer RDD.cache, which keeps in memory. Now already streaming RDDs in memory, it can do joins in memory itself. You never have to go to the disk. So those optimization we can. So the question was how fast this joins going to be, depends upon infrastructure, and again we can cache the RDDs into the memory, then both joins are done in the memory itself, which can speed up your joins fast. Yeah.
Spark now supports data frame also.
Sorry?
Spark now supports data frames also.
Yeah.
Does it make sense to do an RDD join or should you?
Okay, so nice question. So we'll not go and get into it because we may have one. So there was one request for doing a data frame session. So I can say data frame internally is a wrapper around RDD.
Yeah.
So there is a 2 RDD method on top of it, which means I think over the time for structured data we will going to do data frame joins because they are more optimized compared to RDD joins. So that's kind of a thing we are going to do. Maybe so there was one session from in the recent Spark Meet conference. They are saying data frames are around 4x faster than normal RDD operations, provided that your data is structured. So that is the only thing, because data frames are supposed for only structured data. Right? Okay, so any other questions? Yeah.
Did you actually mean that RDD join you can do on unstructured data?
Sorry?
You were trying to do an RDD join on an unstructured data?
So here RDD join unstructured data means that in the data frames you are supposed to give the names to the columns, and that's how they figure it out how to optimize. So it's kind of a schema. Yeah, so these are more ad hoc jobs.
That's the best. The data frame model both of those RDDs. Than a join.
When you have to structure it, that is it.
Yeah. So the idea here is that to create a data frame, it needs a schema different. It needs something called struct type schema object with the RDD data. But when you do RDD joins, it do not need that schema object where it needs to know what's structure. You can say args of 0 or field of 0, do a combination of that 0 thing. It do not need for a schema to be there. So RDD join is more of a very ad hoc, and also where I don't know really the schema till I do it. Data from more of saying I know already the schema.
But
Let us
you
get.
still know what you're joining on, right?
Yeah, joining one I know, but I'm saying this is schema across the whole data. Schema across the whole. Yeah, but data frames are interesting. Yeah, okay, we'll not get into it. People say we already learned RDD now. There is new thing.
For the schema, like you have defined the class.
Yeah.
Right. So in class itself, like if I perform a SQL join there instead of the transform function, how different from that?
So are you asking how to do SQL in the streaming?
So what I'm saying is that like you are joining based on a stream RDD and a batch RDD.
Yeah.
And you're applying a transformer function there.
Correct.
So instead of applying a transformer function, you have already defined a class there.
Correct.
And perform like sparse SQL join there.
Yeah.
So will it be better or this?
Okay, so but can I say that is the RDD join is better than SQL join? Is that the thing? Now the difference between RDD join and the SQL join or any kind of structural join is that when you do structural joins, there is an optimizer kicks in to make it faster. So in the SQL, actually there is no Spark SQL per se anymore. Spark SQL is on top of data frame these days. So there is an optimizer. What it does is it's in the multiple levels, right from reading data to doing actual joins. There's a lot of things they do. When you do RDD join, you are your own. So it says that you know what is structure, you know is it the right way to do, you know how to do partition, everything is up to you. When you do anything above the RDD, that SQL or data frame, there is an optimizer in between which can do a lot of things for you. So that's only the difference. So RDD join is kind of a very raw form of doing things. SQL and data frames is a layer on top of it. Then there is a optimizer in between. You don't get that advantage of optimizer if you do RDD joins. If you do SQL join, you get the advantage of. Again, what optimizer exactly does depends on the different cases, but you may get better performance.
That
Joins. Yes. You can ask why you want to do RDD joins. Okay, there are a lot of places we want just to do RDD joins, but again, so the optimizer is also sometimes useful.
There's a discussion at least the Spark community that
Yeah.
we will be using RDD directly now.
Yeah.
Because of the availability of the other things.
Yeah, so yeah, there is one, that's what I'm saying. There is one talk in the conference 2 months back or 1 month back, I think. They were saying use data frames, don't use RDDs, most of the cases. Yeah, data frame, RDD was new 1 year back, now it's a data frames, we don't know what is there next year. So we have to wait and watch what exactly we want.
But RDD is the basic building block, right? It's always better to start there and then move to the
Yeah, so here the question is more of what we want to run in production. Finally. So again, then you have multiple layers of abstraction. Now, only advantage of abstraction is that someone else will do optimization for you. That's only the difference. If you say RDD or anything else, RDD we do our own optimizations.
But from your engineering point of view,
Yeah.
too much abstraction might lead to tough debugging.
Yeah, of course. So I was working with a Spark SQL in the current consulting job, and SQL throws some kind of errors which is saying which RDD you are coming to come. I don't know. I have to select star from this. I'm trying to join. I'm saying, wait, this RDD is not found. Of course, right? So yeah, there is always this issue of converting a SQL kind of language to, even we seen in I think Hive also. Right? When it tries to do joins, it does a MapReduce join, and then suddenly you say, okay, what I'm trying to do here. Right? That of course is there, but again, there is a nice thing to write SQL. Right? Everyone knows SQL. Okay. Any other questions? So good questions. Now this one I will just explain and we'll go forward. Okay, so what is I want to try to do here is that I think how many of you heard window operations? What is a window operation? I think you have an idea. So what is a window operation is that it is a multiple batches at a time kind of a thing. It's similar to state, but it's a little bit different. So state normally kept for a long time. Now window, the difference is it moves as the time moves. So that's one of the difference. So which means here what I'm trying to say is that there is an original DStream which is batched by time 1, time 2, time 3, which means maybe for every 5 seconds there is something. But what I want to say is that there are some calculations you want to do it for last 30 minutes. Not all. Maybe you want to do some processing every 5 minutes and dump the output. But there are some operation I want to do for last 30 minutes. It's not like state forever. It's like last 30 minutes. That last 30 minutes we normally call as a window. So how to create a window out of the stream is very simple. You rather than taking one RDD, take multiple RDDs, make a union out of it, then you get a window. Actual implementation is simple, so simple. So what you do, you get an RDD for each batch, right? If you say window, you get all those RDD, make a union, there's a union operator on RDD. That RDD will be a window RDD. And you can
sliding window?
It's a sliding window. So there are two actually things you can say which time and how much time it has to be sliding. And it has to be multiple of the batch time. So it's a sliding window operation. Now, I'll just show you the code. There is only one difference. We'll do the window word count or something. Okay. Now, if you see, rather than saying reduce, I can say reduce by key and window. So what I can say is that don't reduce for each 5 seconds. You can say reduce after maybe 30 minutes, which means I want to find out the word count for last 30 minutes, not for each batch. Each batch you keep on doing mapping and those kind of things. But reduce you only do for 30 seconds. And what are the two parameters it takes is for after kind of how much batch size you have to do the window, which means how big is the window. The second parameter is how much after how much time you have to slide. So these are two parameters. Here I'm saying is for every 10 seconds you slide, but last 30 seconds what I want. Make sense? Alright, but if you have never done window, maybe it's new to you. But what I'm trying to say is that rather than limiting yourself for a single batch, you can say last given time. Then that batch will be, you can do some. Again, this also needs a checkpointing. The reason is that it has to, now one more thing you have to remember is that is for performance. Since it has to give all the data for that window, you have to have the resources. Right? You have to keep those RDD around, otherwise you cannot do the window operations. Alright, but for what I'm trying to say here. Okay. Now with that, I think I had one more example, but that is extra, which is not in Meetup, so we can skip it. Right. Okay. So that completes, we say, introduction to Spark Stream. I think it itself is a little bit advanced for most of the people here. That's what I'm feeling, but I think almost everyone got an idea what is a streaming means. So biggest part what I wanted to show you is that it's exact same API. You can literally pick up Spark Streaming in half an hour to 1 hour and start writing code with it. The reason is that there is no new API to learn. Of course, there are a lot of specific infrastructure and other things you have to consider. Maybe we'll talk about that in the future sessions. So this kind of gives you a overall idea that what's the streaming is and how exactly it blends inside the Spark ecosystem. Okay, so these are the references. There is one talk from the one of the Databricks guys for Spark streaming. You can go through it. So this is the second link where it compares between. He is one of the core committer of Storm. How Storm is different from the Spark streaming, and this is the your wiki where you can find all the benchmark and those kind of things. So normally I don't put references, but here you need references. You have to go through a lot of things before you make okay what is good. Okay, now what we do is that if there is no more questions, we'll stop. Okay, you can ask questions. We will break for let us say 5 minutes, very small window. Then we'll come back at 12:35. We have one more session where there is a experience sharing session, and also there is a lunch. There's a pizza. So make sure that you are there around 1:30. I think that's what it will come. So please take pizza. At that point of time, we can talk and we can discuss also. Okay, thank you. So we'll break for 5 minutes.